Welcome to the course on Python for data analytics, machine learning and generative AI. In this video, we are going to learn about feature engineering and outliers, one of the most important steps in the data analysis and machine learning process. In this session, we will cover mastering feature engineering and selection, the hierarchy of data refinement, feature engineering lifecycle, feature selection methods, outlier analysis, how to differentiate the outlier and how to detect outliers. Feature engineering is the process of preparing and improving raw data so that machine learning models can understand it and learn better from it. In simple terms, it means turning messy, real-world data into meaningful input features by cleaning data, handling missing values, encoding categorical data, scaling numbers, creating new features and removing irrelevant ones. Good feature engineering helps models become faster, more accurate, easier to interpret and less prone to errors. Let us see feature engineering in detail. At the outermost level, we have feature engineering. This is the overall architecture of data preparation. Here, messy, real-world data is transformed into meaningful inputs by handling missing values, encoding categorical variables, scaling numerical features, and creating new variables. Moving inward, we reach dimensionality reduction. This is a strategic step used when data sets contain a very large number of features. Dimensionality reduction technique converts high dimensional data into a lower dimensional space while preserving as much information or variance as possible. At the core, we have feature selection. This is a more targeted tactic. Instead of transforming data, feature selection simply removes irrelevant or redundant features while keeping the original values unchanged. Together, these three layers form a structured approach to data refinement. Feature selection is a subset of dimensionality reduction, and dimensionality reduction itself operates within the broader framework of feature engineering. As data sets grow larger, they often contain an increasing number of features. While more data may seem beneficial, too many features can actually create serious problems. This challenge is known as the curse of dimensionality. With many features, data points become sparse and scattered, making it difficult for models to identify meaningful patterns. After feature refinement, the same data becomes clearer. By selecting and reducing features, we preserve the true signal and remove unnecessary complexity. Reducing complexity is essential for four key reasons. First, computational cost. Excess features significantly slow down training and increase memory usage. Second, overfitting. When models are exposed to too many irrelevant variables, they tend to memorize noise rather than learn real patterns. Third, interpretability. Simpler models are easier to understand, explain and trust, especially in business and regulatory environments. And finally, accuracy. Removing noisy and irrelevant features often improves model performance rather than harming it. Let's now see the feature engineering lifecycle. The lifecycle follows a structured yet iterative approach. The first step is data cleaning. Here, we correct errors, handle missing values, remove duplicates, and manage outliers. Clean data ensures that models are not learning from noise or incorrect information. Next is the data transformation. In this stage, we prepare data into a usable format through scaling, normalization, and encoding. For example, numerical values may be standardized and categorical values may be converted into numerical representations. The third step is feature extraction. This involves deriving new features from existing data. Example, extracting day, month or year from dates, calculating ratios or generating aggregated values that capture hidden patterns. After extraction comes feature selection. Here we identify and retain only the most relevant features. Irrelevant or redundant variables are removed to reduce complexity, prevent overfitting, and improve model interpretability. Finally, we have feature iteration. Feature engineering is not a one-time activity. Based on model performance and feedback, features are refined, added, or removed to continuously improve results. When working with high-dimensional data, one critical decision we must make is how to reduce complexity. This brings us two important strategies: feature selection and feature extraction. Both fall under broader concept of dimensionality reduction, but they serve different purposes. The key question to ask is, do we want to keep the original variables? If the answer is yes, we apply feature selection. Feature selection works like a filter. Here, we retain the most relevant features and remove redundant or irrelevant ones without altering their original meaning. Feature extraction acts as a compressor. Here, original variables are combined or transferred to create entirely new features. Feature selection is about choosing the most useful inputs from a model so that it learns faster and performs better. The first method is filter methods, which work independently of any machine learning models. They are very fast and are usually applied at the beginning, especially when the data set is large. But they look at each feature separately and may miss relationships between variables. The second method is embedded methods, where feature selection happens during model training itself. These methods create a balance between speed and accuracy and are commonly used in models like decision trees and random forest. The third method is wrapper method, which tests different combinations of features by repeatedly training a model. Although they can give high accuracy on small data sets, they are slow and can easily lead to overfitting. As we move from filter to wrapper methods, model interaction and computational cost increase. So, the choice depends on the data size, model complexity, and performance goals. On seeing the real-world application, in healthcare, they help researchers identify specific disease-related genes such as those linked to leukemia from thousands of possible candidates, which lowers diagnostic time and cost. In image-based systems, instead of relying on manual tags, data is indexed using visual features like texture and shape, making it possible to search through very large image databases efficiently. In cybersecurity, these methods support the detection of unusual or suspicious patterns hidden within millions of normal network activities, helping organizations respond to threats early. In natural language processing, they are used to manage the extremely large vocabulary of human language by reducing the number of word features, which makes text analysis faster and more accurate. Together, these applications show how intelligent feature handling turns complex, high-volume data into actionable insights. Most data points follow a familiar pattern, often forming a bell-shaped distribution, but occasionally a value appears far from the rest. That unusual point is the suspect. Outlier may be caused by data entry error, faulty sensors, or rare but meaningful events. So they should never be removed without investigation. Detecting them early helps improve data quality and prevents models from being misled by extreme values. Let's now see the concept of outlier in detail. In data terms, an outlier is a value that differs sharply from the rest of the observations. Some outliers appear in a single variable such as an age value of 150, which clearly does not fit normal human limits. Others only become visible when two or more variables are considered together. For example, a very young child reported to have an unusual high salary. Not all outliers are the same, and understanding their type help us decide how to handle them. The first type is global outliers, also called point anomalies. These are individual values that clearly stand apart from the rest of the data, such as a very high weight in a data set where most values are much lower. The second type is contextual outlier, where a data point may appear normal at first glance but becomes unusual when the context is considered. For example, a high temperature is expected in summer but would be surprising in winter. The third type is collective outlier, which do not stand out individually but appear abnormal when a group of related points is examined together, such as a sudden pattern of unusual network traffic. In visual detection, symbol plots help us quickly spot unusual values. A box plot highlights extreme values using whiskers and quartiles, making it ideal for finding outliers in a single variable. Histograms show how data is distributed and reveal values that appear far away from the main cluster. Scatter plots are especially useful when working with two variables, as they expose points that break the overall trend. In statistical deduction, which brings in mathematical rules, when data follows a normal distribution, the set score measures how far a value is from the mean in terms of standard deviation. Values lying beyond 3 standard deviations on either side are flagged as potential outliers. In phase 3, we handle outliers using the removal method, also called trimming. Here, the outlier row is completely removed from the dataset. This method is fast and easy and helps remove noise from the data. However, it also reduces the size of the dataset and may lead to loss of useful information. We use this method only when we are sure that the outlier is an error, like a data entry mistake, or when it does not add any value to our analysis. Let's now summarize the key ideas of feature engineering and outlier. Feature engineering is the complete process of preparing raw data for machine learning. Feature reduction is important because having too many features increases computational cost, causes overfitting, makes model hard to interpret, and often reduces accuracy. The feature engineering lifecycle follows 5 main steps: data cleaning, data transformation, feature extraction, feature selection, and continuous feature iteration based on model feedback. Feature selection keeps the original values and removes irrelevant ones, while feature extraction creates new features by transforming or combining existing data. Finally, outlier are unusual values that can mislead models. Trimming removes these outliers only when we are confident they are errors and do not add any useful information to the analysis. So, let's open Jupyter Notebook and write some Python codes together and bring the concept of feature engineering and outlier deduction concepts to life. Thank you.